here to start the lecture series of the Mathematics 1. Today our topic is partial derivative, lecture number 8. In the last sessions we are discussed mixed theorem, chain rule, implicit differentiation. So today we are start from the partial derivative, lecture number 8, homogeneous function. An expression of the form a0 x raised to n plus a1 x raised to n minus 1 y plus a2 x raised to n minus 2 y square plus up to an y raised to n is every term of nth degree is called homogeneous function of the degree n. Now it can be also written as x raised to n a0 plus a1 y by x plus a2 y upon x whole square up to an minus 1 y by x raised to n minus 1 plus an y by x raised to n. So we are taking x raised to n phi of y by x is a function of f of x y, which can be expressed as x raised to n phi y by x or y raised to n phi x by y. Is called homogeneous function of degree n in x and y. Now homogeneous function. A function f of two variables x and y is said to be homogeneous function of degree n if by putting x equal to 2x and y equal to ty we get the value t raised to n f of xy for any real number of t. Now, what is our f of tx, ty, t raised to n f of xy? We say that as a mathematical term, f of tx, ty, if we are replacing with the x and y, then we get t raised to n f of xy. A function f of three variables, that means x, y and z, is said to be a homogeneous function with degree n if putting x equal to tx, y equal to ty and z equal to tz. So, function xyz becomes t raised to n f of xyz for any real number of t. That means f of tx, ty, tz equal to t raised to n f of xyz. Examine whether the function u equal to x raised to 2 by 3 minus y raised to 2 by 3 x raised to 5 by 4 plus y raised to 5 by 4 is a homogeneous, and if yes, then it's a degree. Here u equal to f of x, right? X raised to 2 by 3 minus u raised to 2 by 3 x raised to 5 by 4 plus y raised to 5 by 4. Put x equal to 2x and y equal to ty. So we getting tx raised to 2 by 3 minus ty raised to 2 by 3 upon tx raised to 5 by 4 plus ty raised to 5 by 4. Take the common value of t. We get t raised to 2 by 3 upon t raised to 5 by 4 into u. So it is t raised to 2 by 3 minus 5 by 4 and multiply with x raised to 2 by 3 minus y raised to 2 by 3 x raised to 5 by 4 plus y raised to 5 by 4. So we get t raised to minus 7 by 12 and as it is function. So t raised to minus 7 by 12, that means u of xy. U is a homogeneous function with the degree of n equal to minus 7 by 12. Now, examine the function of u equal to sin inverse x minus y upon under root x square plus y square. Is a homogeneous, and if yes, then find the degree. Now, u xy equal to sin inverse x minus y under root x square plus y. Putting x equal to 2x and y equal to ty. U of tx ty sin inverse tx minus ty under root t square x square plus t square plus into y square. Sin inverse tx minus y, we are taking t from the under root 2. So we get t under root x square plus y square. T cut out, so we get sin inverse x minus y upon under root x square plus y. So t raised to 0 sin inverse x minus y upon x square plus y square. So function is homogeneous with degree n equal to 0. Now examine whether the function u equal to tan inverse x cube minus y cube upon x plus y, and it is homogeneous, then find degree. Similarly, we taking u tan inverse x cube minus y cube upon x plus y, x equal to 2x, y equal to dy tan inverse t cube x cube minus t cube y cube upon tx plus dy. Taking t cube common from the numerator and t common from the denominator, we getting t square. Okay. U of tx dy is not equal to t raised to n to xy. So this function is not a homogeneous function. Thank you. We are discussing about the homogeneous function. Now, Euler's theorem on homogeneous function. Differentiate equation 1 partially with respect to y. We get del u by del y equal to x raised to n 5 dash y by x into 1 by x. Okay. So del u by del y is x raised to n minus 1 5 dash y by x. Y del u by del y equal to x raised to n minus 1 y 5 dash y by x. We are multiplying y with both the sides. Now, adding equation number 2 and 3, we get x del u by del x plus y del u by del y and x raised to 5y by x minus x raised to n minus 1 y 5 dash y by x plus x raised to n minus 1 y 5 dash y by x. So, x del u by del x plus y del u by del y equal to nx raised to n theta, nx raised to n 5y by x. So, x del u by del x plus y del u by del y equal to nu, because x raised to n 5 by 5 y by x is u, hence it's true. Generalization is if u is a homogeneous function of the x1 up to xk with the degree n, x1 del u by del x1 plus x2 del u by del x2 plus xk del u by del xk equal to nu. Corollary, if u is a homogeneous function with the degree xy with the function of xy and degree n, x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square is n minus 1 u. If u is a homogeneous function of x and y of degree n, then x del u by del x plus y del u by del y equal to nu. Since u is a function, homogeneous function degree n, u can be written as u equal to x raised to n 5y by x, that is our equation 1. Now differentiate equation 1 partially with respect to x. So we get del u by del x equal to nx raised to n minus 1 5 y by x plus x raised to n 5 dash y by x minus y upon x square. Now del u by del x equal to nx raised to n minus 1 5 y by x minus x raised to n minus 2 5 y 5 dash y by x. So x del u by del x equal to nx raised to n 5 y by x minus x raised to n minus 1 y 5 dash y by x, that is our equation 2. Here we multiply x from the both sides. Verify Euler's theorem for the function u equal to x square plus y square plus z square raised to minus 1 by 2. Here u is x y z, x square plus y square plus z square raised to minus 1 by 2. Putting x equal to dx, dy and dz. So we get t square minus 1 by 2 x square plus y square plus z square minus 1 by 2. So t raised to minus 1 u of x y z. So this function is homogeneous with the degree minus 1. By the Euler's theorem, x del u by del x plus y del u by del y plus z del u by del z equal to nu. So x del u by del x plus y del u by del y plus z del u by del z equal to minus 1, because here n equal to minus 1. Now verify for this. See, x del u by del x plus y del u by del y plus z del u by del z equal to minus 2. Now we taking u, x square plus y square plus z square raised to minus 1 by 2, that is our equation 1. Now we are differentiate the u with respect to x. So we get minus 1 by 2 x square plus y square plus z square raised to minus 3 by 2, and differentiation of x square is 2x. Similarly, del u by del x we get it. Solve this thing, minus x square plus y square plus z square raised to minus 3 by 2 into x. Now x del u by del x, so minus x square plus y square plus z square raised to minus 3 by 2 x square, equation number 2. Similarly, we get For the del u by del y del u by del y is minus x square plus y square plus z square raised to minus 3 by 2 y square. That is our equation number 2. Same for the del u by del z. We are differentiate u with respect to z, then we get minus 1 by 2 x square plus y square plus z square raised to minus 3 by 2 into 2z. We get del u by del z equal to minus x square plus y square plus z square raised to minus 3 by 2 into z. So what is our z? Z del u by del z minus z x square plus y square plus z square raised to minus 3 by 2 into z raised to 2. It's our equation number 4. Adding 2, 3 and 4, we get minus x square plus y square z square minus 3 by 2 x square minus x square plus y square z square minus 3 by 2 y square minus x square y square z square raised to minus 3 by 2 into z square. We are taking common minus, getting x square y square z square raised to minus 3 by 2, and second bracket is x square plus y square plus z square. The power addition, so we get x square plus y square z square raised to minus 1 by 2, and it is our u. Hence, Euler's theorem is verified. Now we are taking example. If z equal to xy, function of y by x, then show that x del z by del x plus y del z by del y equal to 2z. Zxy equal to xy f of y by x. Putting x equal to tx, y equal to ty, z equal to tx, ty. Tx, ty f of ty by dx. So we get z tx, ty equal to t square xy f of y by x. T square. What is our xy f of? That is our function z f of x, zxy. Z is a homogeneous 50 degree n equal to 2 by the Euler's theorem. X del z by del x plus y del z by del y equal to nz. But what is our n? N is from the modified Euler's theorem. First of all, we see that homogeneous function. Then we are applying Euler's theorem, and then we are using modified Euler's theorem. First of all, what is homogeneous function? If we are applying tx and ty and we getting a t raised to n f of xy, then function is homogeneous with the degree n. Okay, now it's verified that homogeneous function. After that, we are applying Euler's theorem for the homogeneous function. And what is our Euler's theorem? X del u by del x plus y del u by del y equal to n u, or x square del square u by del x y del x square plus 2xy del u by del x del square u by del x del y plus 2y del u by del square u by del y square is our Euler's theorem. Now we are applying modified Euler's theorem. Corollary: if there is a homogeneous function of degree n is x, y and z, then f of u we get is x del u by del x plus y del u by del y equal to n f of u upon f dash u. Corollary is, if z is a homogeneous function with a degree n in x, y and z are equal to f of u, then x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square equal to g of u into g dash u minus 1. Okay, both are the generalization form of the modified Euler's theorem, where g of u equal to n f of u upon f dash u. Now we taking example. If u equal to sin inverse x raised to 1 by 4 plus y raised to 1 by 4 upon x raised to 1 by 5 plus y raised to 1 by 5, then prove that first x del u by del x plus y del u by del y equal to 1 by 20 10, and x square del square u by del x square plus 2xy del square u by upon del x del y plus y square del square u by del y square equal to 1 by 400 10 u 10 square u minus 9u. Clearly, here we see that the modified Euler's formation. Okay, now we taking modified Euler's form. We first of all we take u equal to function equal to sin inverse x raised to 1 by 4 plus y raised to 1 by 4 x raised to 1 by 5 plus y raised to 1 by 5. Putting x equal to 2x and t by, we getting t raised to 1 by 4 x raised to 1 by 4 plus t raised to 1 by 4 into y raised to 1 by 4 upon t raised to 1 by 5 x raised to 1 by 5 plus t raised to 1 by 5 x raised to 1 by 5 in the bracket of sin inverse. To common take t raised to 1 by 4 and upon t raised to 1 by 5, we get t raised to 1 upon 20 x raised to 1 by 4 y raised to 1 by 4 x raised to 1 by 5 plus y raised to 1 by 5. U is not a homogeneous function here because we are not easily getting the value e raised to n f of xy. So we are taking z equal to sin u. X raised to 1 by 4 plus y raised to 1 by 4 x raised to 1 by 5 plus y raised to 1 by 5. This is a homogeneous function with the degree n equal to 1 by 20 and z equal to f of u sin u. By the modified Euler theorem, first is x del u by del x plus y del u by del y equal to n f of u upon f plus u. What is our n? N is 1 by 20. What is our f of u? It is sin u, f dash u, cos u. X del u by del x plus y del u by del y equal to 1 by 20 into tan u. Hence, prove the first result. Now for the second result, x square del square u by del x square plus 2xy del square u upon del x del y plus y square del square u upon del y square equal to g of u g dash u minus 1. For g of u equal to, what is our g of u? That is f dash u upon f of u into n. We get 1 upon 20 tan u, 1 upon 20. What is our g dash u? That is 1 upon 20 x square u minus 1. So we taking 1 by 20 outside the bracket, we get 1 by 400 tan u x square u minus 20. 1 upon tan u, 1 upon 400 tan u. Formation of x square u is 1 plus n square u minus 20. So we get 1 by 400 tan u n square u minus 90 is the second result. Now, next example, if u equal to log x square plus y square upon xy and prove that first result x del u by del x plus y del u by del y equal to 1. And second, x square del square u by del x square plus 2xy del square u by del x del y plus y square del square u by del y square equal to minus 1. Now, first of all, u equal to log x square plus y square upon x plus y. Putting x equal to tx and ty, we get log t square x square plus t square y square upon tx ty. Taking t common, we get t square x square plus y square upon tx plus y. So it is log t x square plus y square x plus y. Now, u is not a homogeneous function, so we get z equal to e raised to u as per the solving formula equal to z x square plus y square upon x plus y, which is a homogeneous function with the degree n equal to 1 and function f of u is e raised to u. So by the modified Euler theorem, x del u by del x plus y del u by del y equal to n f of u upon f dash u, n equal to 1, f of u e dash u, f dash u e dash u. So we get only 1. Hence, first result is proved as per x del u by del x plus y del u by del y equal to 1. For the second result, x square del square u by del x square plus y plus 2xy del square u by del x del y plus y square del square u by del y square equal to g of u g dash u minus 1. What is our g of u? It is 1 and g dash u is 0 minus 1. So we get it minus 1. Hence, second result is also true. Some examples for the Euler theorem and modified Euler theorem. Show the some modified Euler theorem using